Well, welcome back, and we've got a fun topic tonight titled Summation Notation. And what I want you to do is kind of just box in these first three letters of the word summation, and the first three letters spell the word sum. And all sum means to do, hopefully you know, is simply to add. So if you can add, you're going to be in great shape tonight. So mathematicians use notation to reduce the amount of writing they do. I think we could all relate to that. So here's what we're going to make sure we jot down here. The first letter of summation is S, and the Greek letter for S is read sigma. Capital sigma looks like this. So this is the notation we're going to use for summation notation. And again, summation starts with S. The Greek letter for sigma is right here. So let's make sure we have this written out perfectly. The sum of the first n terms of a sequence can be represented by, and again, make sure we have this notation copied down. So this here is our sigma, and here's how we're going to read it. So in quotes, again, write this down, please. It is read the sum of a sub k from k equals 1 to k equals n. So not only do we want to be able to do mathematics correctly, we also need to be able to speak and communicate it correctly. So let's just go through this one last time. This is read the sum, that's our sigma, summation notation. So the sum, now here's who you're summing, a sub k, anybody that's lowered, you always say sub, from k equals 1 to k equals n. Now you notice we only write the k equals 1 in the bottom, we don't put the k at the top. A few more tidbits here. K is known as the index variable. Okay, so there's probably a new word for us. K is the index variable. And here's how we attack this. In this case, we will start by replacing k with 1 and end at k equals n and add the result together. So we're going to start by substituting this k value of 1 in. We're going to plug in all the numbers up to n and add those together. So let's put that into practice. Evaluate the sum. So again, we want to make sure we can read this out loud. So this is read the sum, this is our sigma, the Greek letter sigma for S, the sum of 2 times k from k equals 3 to k equals 6. So here's how we attack this one. We're going to start at the bottom with our index. So again, this is called the index. This is where you start. We're just going to start by substituting the number 3 into the letter k. So I'm going to get 2 times 3. Now, sigma meant sum, so we're going to add, and we go all the way up to 6. After 3 comes the number 4. So 2 times 4 plus 2 times 5 plus 2 times 6. So we start at this lower index of 3. We're going to end at 6, and sigma, or summation, just means to add each term together. So 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, and 12. And again, my goal is just to add them together. So that gets me a 14 plus a 10 plus a 12, looks like 36. And that is the sum of 2k from k equals 3 to 6. All right, let's try another one. Again, this is the Greek letter sigma. So this is read the sum of j squared from j equals 5 to j equals 7. So in this case, we start with our index of 5. We're just going to substitute it in. So 5 squared. Sigma means sum, so add, and you're going to go from 5 to 7. So 6 squared plus 7 squared. And then we're just going to add those together. 25 plus 36 plus 49. And that leaves me with a sum of 110. So again, summation notation, or sigma, just means to add. All right, one last quick example before we change it up a bit. So why don't you pause it, you try it, don't cheat yourself, and see if we get the same thing. Good luck. So I had a 1/2 plus 1/3 plus 1/4, and then I said, okay, in order to add fractions, I need a common denominator. I went with 12. So I said, all right, to make this a 12, I'm going to multiply by 6 over 6, 4 over 4, 3 over 3. So that leaves me with a total of 6 plus 4 plus 3, 13 over 12. Now our fourth example is going to throw some stuff in from the other day. Consider the sequence defined recursively. So let's go ahead and box that word in, recursively. Remember that uses a previous term. By, and here's our rule, a sub n equals a sub n minus 1 plus 3 times a sub n minus 2, where a sub 1 equals 1 and a sub 2 equals 2. Find the value of the summation a sub k from k equals 4 to k equals 6. All right, so I'm going to first start with my summation. So I'm going to say, okay, the question's really saying find, let's see, begin at the index, a sub 4 plus a sub 5 plus a sub 6. Well, that sounds easy enough. All I have to do is figure out the fourth term, the fifth term, and the sixth term, and add them together. Now, how do we get those terms? Well, we use that recursive definition. We already know a sub 1, we know the first term, and we know the second term. So I'm going to go ahead and make my table, and I'm going to start with the third term then. So as you recall, when we did recursive, we said, okay, these are the n values. So I know when n is 1, my answer is 1. When n is 2, my answer is 2. Now I have to do some work here. So I'm just going to write the rule down. A sub n equals a sub n minus 1 plus 3 times a sub n minus 2. So if I want the third term, that's a sub 3 equals a sub 3 minus 1 is really a sub 2 plus 3 times a sub 3 minus 1. So that's 3 times a sub 1. Now again, the more steps you show, the easier this is. A sub 2 is actually 2 plus 3 times a sub 1 is 1. So 3 plus 2 gets me a total of 5. Now I need the fourth term. So I couldn't get the fourth without getting the third, obviously. So fourth term, so that's a sub 4 equals a sub 4 minus 1 is really a sub 3 plus 3 times a sub 4 minus 2 is really a sub 2. So I'll keep going here. A sub 3 is 5 plus 3 times a sub 2, and a sub 2 is 2. So that's 5 plus 6, which gets me 11. All right, now I'll need the fifth term. So a sub 5 is equal to a sub 5 minus 1, so that's a sub 4, plus 3 times a sub 5 minus 2, so that's a sub 3. So let's see, a sub 4 we just had is 11 plus 3 times a sub 3 is 5. So that's going to be 11 plus 15 gets me a 26. And I need one more term because I had to go to a sub 6. So a sub 6 is equal to a sub n minus 1, so that's a sub 5, plus 3 times a sub 6 minus 2, which is a sub 4. So that's going to be 26 plus 3 times 11. So that's 26 plus 33 gets me a total of 59. So now that I know what those terms are, I just need to add a sub 4 plus a sub 5 plus a sub 6. So a sub 4, if I look back, is 11 plus a sub 5 is 26 plus a sub 6, we just said, is 59. And if I add those together, I believe I get a total of 96. Okay, so again, we just use summation notation in a recursive definition. So we're just putting two things together. All right, so now our goal is to go backwards, to write each sum using summation notation. So they gave us a sequence, and we have to go backwards and put it into summation notation. So the first thing you have to do is kind of figure out what the pattern is, what's happening here. Well, I notice everybody is being raised to the fourth power. That is not changing, that's constant. So my gut tells me it's probably something to the fourth power. Okay, well, this is 1 to the fourth, 2 to the fourth, 3 to the fourth, 4 to the fourth. So I'm thinking that this is the sum, obviously we're adding, the summation, of a number to the fourth power, and I want to start that number off at 1. Okay, so 1 to the fourth matches, 2 to the fourth, 3 to the fourth, 4 to the fourth, 5 to the fourth, and I want to end this summation at 7. And I think that does it. And again, you can check and make sure it works out. So I would get 1 to the 4th plus 2 to the 4th plus 3 to the 4th. I'm getting what I'm supposed to get, dot, 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 all the way up to 7 to the 4th. So we just got to come up with a pattern. Many times there's more than one answer, so you don't always have to have the same thing your partner does. But just keep that in mind. Let's try another one. All right, take a look at this sequence. I have 9 plus 16 plus 25 plus some other numbers all the way up to 100. Okay, can you find the pattern? What's happening? Where are these numbers coming from? Well, I'm hoping it's fairly obvious. One answer anyway is fairly obvious. I hope you recognize that this is 3 squared, and this number is 4 squared, and this number is 5 squared. Probably some numbers in between there. This number is 10 squared. So do you think we could write the summation? I hope so. I would say it's the summation of a number squared. Now I used n in the last example. You can pick any number you want. Maybe you like I squared. Starting at what index? What is the first number you want to plug in? Well, I would say from I equals 3, because that would get me 9. What would be the last number I want to plug in? 10. So I would say this is the summation of I squared from I equals 3 to 10. Just take a note, these two variables obviously need to match so you know that you're plugging that number in there. Now, like I said, this is not the only answer. Maybe you got more creative. Let me show you another example. Think about this. Maybe this is a multiple choice question and that's not an option. See if you would agree with this. If my index is 2 and I end at 9, what do you think about I plus 1 squared? Would that work? Well, let's think. If I plug in a 2, that's going to be 2 plus 1 squared. That's going to be 3 squared, which is 9. The next number I would plug in is 3. 3 plus 1 is 4 squared. Plus 4 plus 1 is 5 squared, dot, dot, dot. If I plugged in a 9, 9 plus 1 is 10 squared. Look at that. So like I said, there's more than one option. To me, this one was a little more obvious because I recognized it as a number squared, but certainly I could say it's a number plus 1 squared with different index there. So again, feel free to get creative on these. All right, take a look at this sequence. -6 plus -3 plus 0 plus 3 plus something up to 15. Okay, so I'm going to look for that pattern first. So how did I go from -6 to -3? Looks like a difference of 3, and then -3 to 0. All right, I think I'm onto something. Would you say that's a difference of 3? I added 3. -3 to 0, I added 3. 0 to 3, I added 3. I guess the pattern looks arithmetic to me. It looks like I'm adding a number. So the first thing I did is I said, okay, if it's arithmetic, I know it follows the formula a sub n equals a sub 1 plus the difference times n minus 1. So I said, okay, the rule for a sub n is going to be the first term, -6, plus the difference of 3 times n minus 1. So that's a sub n equals -6 plus 3n minus 3. So what does that get me? The rule for a sub n is going to be -9 plus 3n. Okay, so once I have the rule, I think we're in great shape here. So I'm going to say, okay, well, this sequence is the sum of -9 plus 3n, there's my rule, from an index of n equals what? What number would I first plug in here? Well, if this is the first term, hopefully you're plugging in the number 1. Let's just verify that it works. If I plug in a 1, I get -9 plus 3, which is -6. If I plug in a 2, I get -9 plus 6, which is -3. If I plug in a 3, I get -9 plus 9, which is 0. Looks like my pattern's holding true, and it should because we just followed that arithmetic rule. Now I have to figure out when to stop. So basically I'm saying, I'm just going to write a simple equation. When does that rule, -9 plus 3n, have to equal 15? So I'm going to add that 9 over and say 3n equals 24. Divide out my 3, and I know n equals 8. So that tells me I should stop at 8. And again, we can verify. -9 plus 3 times 8 is 24 is 15. So that holds true. So once you know what the rule is, and you can write, say it's arithmetic or geometric, I would just write the rule and plug it in. All right, let's try another one where we go backwards and write the summation. 3 plus 6 plus 12 plus ... plus 48. And our goal is to express this in terms of summation notation. All right, so again, my goal is to figure out, is there a nice pattern or do I just kind of have to guess? Well, it looks like if I jump from 3 to 6, I either add 3 or I multiply by 2. But I need to be consistent. If I go from 6 to 12, do I add 3 or multiply by 2? Well, I multiply by 2, so that means the adding 3 part's out. So I would say I'm multiplying by 2. Here I'm multiplying by 2. So I guess to me I'm saying, okay, this is a geometric rule. So a sub n equals a sub 1 ratio to the n minus 1. A sub n equals, my first term is 3. My ratio, we just said, is times 2 raised to the n minus 1. So there's the beginning of my summation of 3 times 2 to the n minus 1. So I'm putting the rule in there. From n equals, I believe I'm going to start at 1 because that's my first term. And again, I can verify it. 1 minus 1 is 0. Anybody to the 0 is 1. And 1 times 3 is 3. Now I have to go up to 48. So again, it's very simple. You just set your equation equal to 48 to figure out what the nth term is. All right, now solving this. We've practiced solving these equations for quite a while now. Remember that this exponent is only on the base. Box it in to help yourself. I'm going to have to first divide both sides by 3. So that leaves me with 16 equals 2 to the n minus 1. Now from here, this is great practice because this leads us into two different directions. There are two ways to solve this. Well, actually 3 ways. You could use a calculator. The first way is to get common bases. So I could say 16 is really 2 to the what power? See, 2 squared, 2 cubed, 2 to the 4th equals 2 to the n minus 1. So let's make a note that's common bases. Once the bases are equal, we cancel those and we say 4 equals n minus 1. Therefore, the nth term has to be 5. Okay, now we could also use logs because this is exponential, remember, when the exponent's a variable. So let's solve this out as well. 16 equals 2 to the n minus 1. You simply take the log of both sides. So if I log of 16, now I have to use properties. I have to bring that whole exponent down, so watch your parentheses. N minus 1 log of 2. Okay, we've been doing that for quite a while now. I'm going to divide over the log of 2. Okay. Now, I don't have a calculator in front of me, so I'm going to go backwards on my change of base. Remember, the base goes on the bottom. So this can be rewritten backwards from change of base as log base 2 of 16. Okay, so again, I'm just going backwards from the change of base. Change of base says this goes in the numerator and this goes in the denominator. Now, this is a number you should know because remember, log really means what power? What power of 2 is 16? Well, 2 to the 4th is 16. And here I still have my n minus 1, so n equals 5. Okay, now, let's say at this point, obviously, you could type in log of 16 divided by log of 2 in your calculator. But again, I'm just kind of reviewing lots of properties we've talked about. Either way, we get an n value of 5. So that means this is the summation of 3 times 2 to the n minus 1 from n equals 1 to n equals 5. All right, now I tried to tweak some properties on you right here. Notice there's this big fat 3 in front of my summation. Anytime you see this, guys, here's what we need to do. We need to put a big bracket around the summation. Okay, because this is really 3 times, there's no plus sign, 3 times the summation of this quantity. So what you have to do is do 3, and we're going to leave this in a nice big bracket and write out your summation. So I'm going to say this is really 3 times 2 minus 1 plus 3 times 3 minus 1 plus 3 times 4 minus 1. And I'm going to close that big bracket. Okay, so order of operations is huge here. You have to first find the summation and then multiply by 3. So I think it's really smart if you just stick a big bracket around there and continue that big bracket through. So we'll go ahead and clean this up. All right, so that's 6 minus 1, that's 5. So that's 3. So we have 5 plus, that's 9 minus 1 is 8. Plus, that's 12 minus 1 is 11. So oops, lost my pen. I believe that gives me a total of 24. Now times that 3 for a final answer of 72. Okay, so order of operations is huge. Keep it nice and neat with that bracket. All right, last example. I have 2 plus 4 times the summation of 2n from n equals 1 to n equals 3. So again, order of operations is huge here. Notice that this is being multiplied. Okay, so you cannot add the 2 and the 4 because it's 2 plus 4 times this quantity. So you do have to multiply first, correct? We're going to multiply those first, and then we'll add that 2 on after. But obviously, you first have to get that summation. So I'm going to say it's 2 plus 4 times the summation. Let's go get the summation. I'm going to plug in a 1, so that's 2 times 1, plus 2 times 2, plus 2 times 3. We'll close that bad boy up. Okay, so I have 2 plus 4. This guy's summation is really 2 plus 4 plus 6 gets me a total of 12. Okay, so now I'm really just following through that order of operations. PEMDAS, parentheses, exponents, multiply, then you can add and subtract. So this is really 2 plus 48 for a total of 50. Well, that does it for our video on summation notation. So we learned a new Greek letter in our alphabet here, and we look forward to some great practice.